Welcome to the class. Yesterday we have discussed about the types of methods for food analysis and the syllabus part and food analysis and testing, the physical analysis, chemical analysis and the microbiological analysis, AOAC, AACC, and the types of methods for food analysis, and we have discussed yesterday the subjective classification. Today we are going to explain about the objective classification in detail. In objective classification, we have the physical, chemical, microscopic and the microbiological classification. Now we will start with the physical classification. Now let us start with the objective methods. Objective methods of food analysis involves the use of instruments and techniques that provide quantifiable means to measure the quantity, reproducible means to produce, and unbiased results means the fair results. These methods are essential for ensuring the accuracy, reliability and consistency of food quality and safety assessments. Now coming to the physical methods of food analysis. It involves the measuring the physical properties of food product using the instrument and techniques. These method provides the objective data and attributes like texture, color, density and other physical characters that are important for the quality control and the product development. There are some common physical methods of food analysis. One is texture analysis. This measures the mechanical properties of the food. Mechanical properties such as hardness, cohesiveness, adhesiveness, chewiness and elasticity. What is the difference between the cohesiveness and the adhesiveness? Adhesion and cohesion are both forces that describe the attraction between the molecules. Both are same, but they differ in the type of molecules they attract. Adhesion means the force of attraction between molecules of different substances. For example, when water is poured on a glass surface, the adhesion force between the water and the glass causes the water to spread out. Whereas in cohesion, the force of attraction between molecules of the same substance. For example, the cohesion force between water molecule causes them to stick together to form a sphere. That's the difference between the cohesiveness and the adhesiveness. In texture analysis, they use the probes and fixtures to apply force and measure the resistance or deformation in the food samples. In penetrometers, measures the force required to penetrate a food sample, often used for the fruits and vegetables. Here force is applied to measure the resistance. Here they measure the force to penetrate a food sample. This is the texture analyzer. This is the penetrometer. This is called the probe. Here the food sample is placed, and in this penetrometer, this is the depth line. We can see it properly with the red mark, and this is the maximum hardness indicator and the reset for maximum hardness. Here are some other probes. Dual cone probe. This is used to measure the internal firmness. See, dual cone means this is one cone and this is the other cone. Conical probe. It is used in the measurement in the consistency of the penetration of the solid sample. This is the cone shape. Coming to the cylindrical probe, measure in the texture penetration on the solid sample. Cylindrical probe. Bloom probe, used for the measuring the Bloom gel strength test. Bloom probe. Flat probe is used to measure the consistency, elasticity, adhesion and spinning on the solid of a size smaller than the tray. This is the flat probe, and these are also several probes used in the various methods of food analysis. Next is rheology. Rheo means to flow, logos means science, ology is the study. Thus the rheology is the science that concern with the flow of liquids and deformation of the solids. Rheology. It measures the flow and the deformation behavior of the food materials. It is important for the products like sausages, gels and doughs. Rheometers. It measures the viscosity, elasticity and the viscoelastic properties of both solids and liquid foods. What is viscosity? Viscosity is a measure of the fluid's resistance to flow. Water has the lower viscosity, 1.0 centipoise, whereas honey has the higher viscosity, around 12 centipoise. Viscometers. It measures the viscosity of the liquid foods. This is the viscometer. Next is the calorimetry and the spectrophotometry. These methods objectively measure the color of the food products. It is crucial for the quality control and the consumer acceptance. Colorimeters measures the color based on the standard color scales. Spectrophotometers, it measures the intensity of the light absorbed by the sample across different wavelengths, providing detailed color information. It measures the color, it measures the intensity of the light absorbed. This is the electromagnetic spectrum. This is the visible light where we can see the colors. The range is from 380 to 700 nanometers. This is the colorimetry diagram. The light source is passed through the slit. Slit is a small gap and the polychromic light is passed through the lens and it is filtered, and after filtration it is going to convert it into monochromic light, and it is passed through the sample. This is cuvite where the sample is present, then it is passed through the photocell and final we will get the output. Here polychromic light and monochromic light is, the polychromic light is made up of many different wavelengths, while monochromic light has only one wavelength. Here we will get the output in the form of signals. Here this photocell is a device that converts light energy to the electrical energy or detects and measures light. In spectrophotometer, we use the light source and the sample is placed and it is passed through the prism and it is connected to the detector. A detector is a device that records the signal and gives the output in the computer as the signal. And this is the mass spectroscopy where ion source is used and magnet is used instead of prism and it is connected to the detector. The difference between the colorimetry versus the spectrophotometry. Coming to the definition, this is the technique we use to determine the concentration of the solution which is having the color. Spectrophotometry. What is spectrophotometry? When a beam of light that passes through the sample, how much light that is absorbed by the chemical substance by measuring the intensity. And what is the wavelength difference? Uses fixed wavelength which is in the visible range, that is from 380 to 700 nanometers. This is the spectrophotometry wavelength is wider range, that is UV and IR range. UV range is from 100 to 380 nanometers, whereas IR is 760 to 3000 nanometers. The sample color will be, it is needed to use the colorful samples, here need to use the colorless samples. Quantification means measurement. It measures three primary color components of light. They are red, green and blue. It measures the precise color in the UV visible light wavelengths. What is measurement? Measures the absorbance of light. What is absorbance? Quantity of light that is absorbed by the solution. Here in spectrophotometry, measures the amount of light that is passed through the solution. Here it measures the absorbance of light. Here it measures the amount of light that is passed through the sample. This is the difference. Moisture content determination. It is very important in food industry because shelf life depends on it. The moisture content affects the texture, shelf life and the quality of the food products. In moisture content, we will see the oven drying. Here the samples are heated in an oven and the loss of weight is used to calculate the moisture content. Carl-Fisher titration. This is the chemical method for determining water content. Infrared moisture analyzers uses infrared radiation to measure the moisture content quickly. This is the Carl-Fisher titration. In this we will have the bigger beaker and the inner burette. This is the inner burette. For this inner burette, at the lower side we will have the semi-permeable membrane where the solution passes through it. We can see the anode here and the cathode here. The food sample or any sample can be placed from this mouth region, and this is the piston burette, and in this we will place the Carl-Fisher reagent. The Carl-Fisher reagent is made up of the iodine, sulfur dioxide, pyridine or imidazole and methanol. The Carl-Fisher reagent is sent to the burette drop by drop with the piston action. Here we are also having the detection electrode. Here the sample and the Carl-Fisher reagent undergo titration slowly. Here our sample will be present, in which we have to determine the water or the moisture content present. Now we'll start the titration equation. This water is from the sample solution and the sulfur dioxide and the iodine is from the Carl-Fischer reagent. Gives the equation sulfur trioxide and the H plus and I minus. This I minus is very important here because due to the presence of I minus ion, current flow will start. Here water content is more, current flow will be also more. At the end point, water content will be finished by adding the KFR reagent continuously. Then there will be no increment in the current flow. That will be our end point. Basically, the moles of water is directly proportional to the moles of iodine present in the titration. In the next step, the sulfur trioxide reacts with the pyridine to form this complex, and this complex reacts with methanol to form this stable complex. Here, the pyridine is added to create the basic environment and form the stable complex, which also acts as the buffer solution. Due to the presence of iodine, there will be the determination of moisture content in the KF titration. This is finally the KF titration method. This is pycnometer and it is made up of glass. If you want to close this, there will be a stopper which fits it properly, and this is the thermometer which allows you to determine the density of the liquid at a specific temperature. And this is the hydrometer or the lactometer, and it is used for measuring the density or the relative density of the liquids. It is based on the concept of buoyancy, and they are typically calibrated or graduated with one or more scales such as specific gravity, flux, etc. This hydrometer is a sealed hollow glass tube. It has a wider bottom portion. It helps in the buoyancy, and this is the lead or mercury for stability. This narrow stem which is present here is with graduations for measuring. The liquid which we want to test is poured in this tall graduated cylinder, and this hydrometer is gently lowered into the liquid until it floats freely. It floats freely without touching the walls of the measuring cylinder. After some time, the point at which the surface of the liquid touches to the stem of the hydrometer, it correlates to the relative density. These hydrometers are calibrated for different uses, such as lactometer for measuring the density or the creaminess of the milk, saccharometer for measuring the density of sugar in a liquid, and alcoholometer for measuring the high levels of alcohol in the spirits such as wine, musk, etc. Now coming to the particle size analysis, it also affects the texture, appearance and the solubility of the food products. In this, the sieving method is the using of the mesh screens. It separates the particles based on size. Laser diffraction uses laser beams to determine the particle size distribution. Microscopy, it provides detailed images and measurements of the particle sizes and the shapes. Thermal analysis, it depends upon the temperature, and it is important for understanding the stability and the shelf life of the food products. In this, we see the differential scanning calorimetry and the thermogravimetric analysis. TSC measures the heat flow associated with the phase transitions, that is example melting and the crystallization. In TGA, it measures changes in the mass as a sample is heated, useful for studying the thermal stability and the decomposition. Now let us see that both techniques. Differential scanning calorimetry. It is commonly used in food industry. For what? To analyze the thermal properties of the food materials. What is the primary function of the differential scanning calorimetry? It is to measure the heat flow into and out of a sample as it undergoes a controlled temperature change. This resulting graph provides various thermal transitions in the food product such as melting, crystallization or denaturation, etc. What are the components of the DSC graph? On x-axis, we have the temperature or the time. It shows how the heat flow changes as the sample is heated or cooled at the control rate. On y-axis, we will measure the heat flow in watts per gram or milliwatts. It indicates how much heat is absorbed or released by the sample during the test. These endothermic processes usually appear as upward peaks, that is positive heat flow, whereas the exothermic processes represents the heat release and the peaks appear downward and it is negative heat flow. This is heat absorbed, this is the heat released process. And for this examples are melting of fat, starch, gelatination example. In this graph we can see the linear heating in the food industry and the modulated heating in the drug industry. Modulated heating and the linear heating are the two different approaches in DSE. Both have advantages depending on the industry. In the drug industry, modulated heating is more commonly used. In food industry, linear heating is preferred. In modulated DSE, modulated heating rate is used, meaning is that the temperature varied in oscillating manner. DSE graph in the food industry provides critical data on how food products respond to temperature changes and the ensuring product quality, stability and its consistency. In linear heating DSE, the sample is heated or cooled at a constant rate. This is the most common approach in the food industry for studying simpler thermal transitions in food components like fats, starches and the proteins, etc. This modulated heating in the drug industry allows for the detailed analysis of complex pharmaceutical behavior, while linear heating in the food industry is a more practical and efficient method for understanding simpler thermal transitions in the food products. This is the TGA instrument. We can see the inlet here and the food sample here and the sample temperature can be tested here, and this is the furnace where the food is heated or cooled. Here the TGA works by measuring the change in the mass of the material. This mass will be changed by the heating or cooled or held at the constant temperature in the controlled environment. It provides critical information on how a material decomposes or loses mass due to the various processes like evaporation, oxidation or thermal degradation, and final output will be produced in the computer in the form of signals. Microscopy. We know well about the microscopes. Microscopy provides detailed visual analysis of the food structure and its composition. Light microscopy, it observes general structure and morphology of the food samples. Electron microscopy, it gives the high resolution images of the food components such as fat crystals and the protein network. Confocal microscopy, it offers the three-dimensional imaging of the food microstructures. This is the confocal laser scanning microscopy. Here we can see the specimen and the mirrors placed and the pinhole, and it is finally connected to the detector where we get the signals. Here the light is passed here and we get the 3D scan of the food sample or anything. This is the high resolution imaging techniques that uses a pinhole and a light source to create the sharp imagings of the sample. Here we see the electrochemical methods. These methods measure electrical properties related to the concentration of the specific components in food. pH meters and the conductivity meters. pH meters measures the acidity or alkalinity of the food samples, and conductivity meters measures the ionic content and the conductivity of the food solutions. This is the pH meter, and the solution which we want to test is placed in this beaker, and we get the readings in this pH meter. And this is the pH meter. This is an instrument that is used to measure the hydrogen ion activity in the solution. That is nothing but to measure activity or alkalinity of the solution. pH level ranges from 1 to 14, and 7 is the neutral value. Before 7, 0 to 7, there will be acid solutions, and 7 to 14 there will be the basic solutions, and this is used to measure the temperature. And this one is the conductivity TDS. TDS means total dissolved solids. This is used to measure the Water quality. TDS is measured in ppm. Between 50 to 150 ppm, water is excellent for drinking. Between 150 to 250 ppm, water is good. Between 250 to 300 ppm, the water is fair. Between 300 to 500 ppm, the water is poor quality and it is not good for drinking. And the last topic is the spectroscopy. Spectroscopic methods measure the interaction of the electromagnetic radiations with the food samples to assess their composition and its structures. Near infrared spectroscopy. This is common analytical method used in the food industry to measure the food characteristics. It is used for rapid, non-destructive analysis of the moisture, protein, fat and other components. Fourier transform infrared spectroscopy. It is a technique that uses infrared light to identify the chemical composition of the sample and its structure. It is used to analyze solids, liquids and the gases. It also identifies the functional groups and the molecular structure. These physical methods are essential for assessing the quality and the characteristics of the food products. They give important information for product development, quality control and regulatory compliances. They ensure the product meets consumer expectations and the safety standards. In the next class, we are going to discuss about the chemical methods of food analysis.